biased, with bias voltage is lower. As smaller the capacitor, usually as higher the parametric effect. Ceramic capacitors also show mechanical effects. So it's called, one is microphony. So if you tap on the board, it will operate like a microphone. And they will also turn the board into a speaker. So if you force audio type AC currents through these ceramic capacitors, and as higher their parametric effects are, usually also as higher the changes of their mechanical properties is. So they can turn easily turn your PCB into a loudspeaker. So if you have one chip, I get often phone calls. Your MPS, MP so-and-so is making audible noises. It's most likely the inductor, because you look at, okay, the IC, nobody believes that that makes noise, and it doesn't. And the larger part will be the inductor. And I tell them, okay, there's a simple way. Just take a small screwdriver. I mean, the old guys might have still an isolated screwdriver to adjust TV sets, but it's pretty much out of fashion. You don't see that. There's a lot of Bernstein screwdrivers around, which are totally of plastic. But you could, if you are careful, also use a normal iron one. Just take the small screwdrivers and put it on the part you're interested and here. So you could use it as a stethoscope and figure out directly where the culprit is. Because it's a mechanical thing, and you can detect it if it's the inductor or the output capacitor. Most time it will be the output capacitor, because that's the one which gets the most audio. So that's a sign. Okay. And so if you compare here 1 microfarad or 4 or 2, now they have a very drastic parametric effect and lose up to 70%, 6.3, I think that's the 10 volts. And as larger the packages get, as less is the parametric effect, as you could expect, because as thicker the dielectric is, as smaller the necessary electric fields. Okay, so here's for 3 different epsilon R's. They are usually in the 2,700 to 6,000 range, so insanely high if you compare them to film capacity or something. So you see the parametric effect. Also, DC bias characteristic for a certain dielectric, not here for different strengths that we can take. That's not all of the bad news. There's an additional effect, usually, no, first of all, how do you measure the capacity on a biased capacitor if you only have a simple handheld RLC meter? I mean, if you have a lab with an $30,000 Keysight biased RLC meter, you are nice, but sometimes you're just on the factory floor or on the lab and you have a handheld RLC meter. And that will blow up if you just put 20 volts on it, because it assumes only AC voltage. What you can do, you take your ceramic capacitor and add an aluminum electrolytic, a thick one in series to it. So the old days, every audio guy had some of these capacitors for his loudspeakers there. If you don't find one, just grab the power supply from your boss computer silver box. There are lots of aluminum electrolytics which have capacity, and put them in series. Put them in series, short them that way, and put with a lab power supply the voltage you're interested in on that capacitor. Then you will have here your 3.3 volt or 5 volt. Here automatically also you get the same voltage. And if you then open that thing up and measure with your cheapo RLC meter, now you will see 2 capacitors in series, but no bias voltage here. Measure actually the series capacity of your 22 microfarad plus it 1,000, 2,000, which will come down to 21.9, whatever. But this will have a very little effect, and you can easily see what the DC voltage impact is on your capacity. If you are not sure that your buyer looked for the cheapest roll and gets some say fake roll where you think, okay, I have good X7R from a certain vendor, but you might then check an Y5V. Then with the same thing, you You can also just heat it, keep the meter on and heat it up with a heat gun or cold spray on a Z5U from the 25 volt centigrade point. Now the capacity will drop on both sides like the rock. So you easily see that. So to compare that. That's some simple tests you can do now if you have the suspicion that there's something fishy about the capacitor. There's even another effect, capacitor effect I don't tell you much about is it's the drop of capacity biased over time. Capacity drops unbiased a little bit, very, very little, but biased, it drops much faster. Not much people have done a test to it. The thing is that the type 2 barium titanate capacitor has a sort of Curie temperature. If you bring these capacitors above this Curie temperature, they reset to their original capacity. They have it at time 0. So here, I used a 22 microfarad 1210 capacitor. It was I think rated about 25 volts or so, and put it on a 3.9 volt bias because I happen to have a super capacitor made out of lithium, which I could hang it there for weeks. And I measured it initially, and then after a few minutes, after an hour, after 100 hours, 600 hours, 1,600 hours. 1,600 hours, which are, I think, 2 months, the capacity actually was down to 15.4 microfarad. And you started also with 21, or close to 21 microfarad. And if you then resolder it, just with a soldering iron, you heat it up, back again, you get the initial capacity. So be careful if you get a board back which has some weird behavior in the field, biased long, even if you unbias it and bias it again, it stays here. Only the heat treatment now will reset it to the original capacity. So be careful if you got something from the feedback. Don't directly desolder the capacitor and measure it. Then you reset it to the original value. Just keep it at whatever room temperature up to 50, 60 degrees centigrade. Not reset it. If you have a suspicion that the capacity change over time has something to do with the problem you have. And that definitely on an LC output filter will change the resonant frequency of that double. Yeah, sure.
Do you think there's a lot of variation, or you theorize there's a lot of variation in that curve between different dielectric formulas?
I think so now, because in a sense, that material starts out with a cubic grid, and in order to get these high dielectric content with these barium in the middle, this cubic grid changes to a complete other grid change at the edge, and that creates these high parametric effects. That also means that there will be a lot of variation. I can only, as say, an old BMW driver say, I mean, with their piezo injectors, which are similar piezo ceramic material, they got a lot of experience that stuff changes over time. So you can expect. If I put it here on a normal, yeah, more question. Sure. Yeah.
What was the voltage rating on this cap?
1210, I think it was 25 volts. So I mean, you can assume 25 microfarad 1210 is a pretty large size cap. So it's not a 5 volt cap also.
This test was just done at room temperature.
Yeah, room temperature. And I was just sitting on my desk here in my lab. So nothing special. So you could see there was a big aluminum electrolytic. Now then the super cap, and then the capacitor was just soldered to one of these big long wires of an aluminum capacitor, and I measured it round trip. Just let it sit there, and I opened it up. Now that I could measure then the bias from time to time. And it is a simple experiment. You could easily also do. And if I put it from a log time screen to a linear time screen, you see that in the first minutes or so, in the first hours, you get the most reactive. After 700 hours to 1,600 hours, there's not that much anymore. And so actually the capacity will not drop to 0. So it will settle out at some point. But over several years or so. But be aware of that. If you have a real safety critical system and you call up your capacitive manufacturer, you will get actually some numbers on it. You say, okay, now I make whatever really safety critical thing, then you will get data on it. But I've not seen that they normally publish that. Okay. Now, what impedance have normal capacitors?
Before you jump,
Yeah, sure.
Are there other capacitor technologies that are better at this?
Sure. I mean, pretty much foil capacitors will lose over time capacity, but in the rate of maybe 1% per year, because the foil will shrink a little bit. Aluminum capacitors mostly decay because their electrolytic is evaporating. So there are 1,000, 5,000 hours aluminum electrolytics. Tantalum, I have no experience with. I would assume they're used in the military. They also last very long. However, tantalum get pretty much out of fashion because there's an additional failure mode in tantalum. Depending on the material you produce them, there could be, if you leave them alone, unbiased dendrite growth, as they short circuit. So can repair them with just a good slush of current, which burns down the dendrites, but there are also chances that they just burn off the wall. So it's so high flames. But that's a thing about ceramic capacitors. Actually, nobody moved around long. And I just 2 weeks ago, I got from my colleague Jens. He had melted with a Bode analyzer, fresh soldered ECVC converter and get pretty good result. And let it sit on over the weekend, and then we measured it, and all of a sudden you get 10 degrees less phase margin. I was like, I'm wrong. It was pretty obvious. Okay, just solder the capacitors and heat them up and look if you still get the original number. Okay. Now to capacitor impedance. I used a TDK CR tool from 2013. My colleagues just let me know that TDK doesn't manufacture any capacitors anymore, which makes it probably not that dangerous to use their software for to show them. But in general, I have the impedance here: 1 ohm, 10 ohms, 100 ohms over frequency. That's 1 megahertz, 1 gigahertz. There's all in the same package: 04 or 2, 100 nanofarad, 10 nano, 1 nanofarad, 100 picofarad. But you can see now that they behave as a capacitor as you expect, and impedance goes down until you hit their self-resonant frequency, when their inductance goes in resonance with their capacitance. And over their self-resonant point, now they become inductive, and at a certain point merge all their inductive impedance. You could think now that above the self-resonant point, which is for 1 nanofarad around 20 megahertz, they are not useful anymore because they turn into an inductor. However, if you decouple something with a capacitor, decoupling means that the capacitor still has low impedance. And here, if you look for the 1 ohm area, 100 nanofarad still would decoupling nicely up to 250 megahertz, and 10 nanofarad, that would even go higher. So only because they change phase and become an inductor doesn't mean that you don't get any decoupling capability. Decoupling capability depends only about the impedance. So you can decouple that stuff up to 1 gigahertz, still using 0402 ceramic capacitor. If you hunt a special single spoor in the whatever range of 1, 2, 3, 4 megahertz, there's one trick you could play: use a capacitor which has actually the self-resonant frequency at or near these frequencies. That will have the lowest impedance, and it can really notch out and high point. So high frequency point, you get a very low impedance short circuit. But beware, we know already now that biased over time stuff. The inductance of these capacitors are all the same because essentially inductance is the integral of the magnetic field. Current flowing through the inductor creates integrated from 0 to infinity, which means you could replace this 442 inductor with a copper block of same size and you will get the same inductance. So it's just think about it. Okay, so we talked a little bit about hot loops, about capacitors. Now jump to EMI coupling mechanisms. Normally you think, okay, now you get a schematic of in this case a step down regulator that's a 4430 input voltage, some input capacitors, inductor, output capacitor, output capacitors here, feedback network, that's back to ground. That's really good. And you think, okay, now if I look at the schematic, I know everything what the circuit does, also EMI. Nothing could be further from the truth. First of all, your elements like capacitors will have parasitic effects like capacity, ESL, ESR, little bit error leakage. And these are parameters you could easily also throw in your SPICE simulation to think, okay, now I have a complete, say, EMI picture. Also not true. You get it, it's a little bit better, but it's still, you get only the currents which are grouped to the wires. In addition, you get some free resistance and inductors on your PC board. The ideal DC-DC converter would have a volume and a size of 0. So then you wouldn't have any EMI problem. But the only issue is that you can't buy ICs and you would have great thermal problems. So that's a problem. But from an EMI standpoint, if you could make it small, then the resistance would go away. That would be nice. But you get free elements also on your PCB, which have resistance and inductance and very big capacity. What makes it even worse is that every node has actually capacity, because on your PCB you rise stuff above PCB level. Now you have terminals of all your points, of your ICs, of your capacitors, inductors, and so on. So they have capacity, and with this capacity, they E-field couple in any other terminal on the PCB. So you have an enormous amount of coupling, which you think now it's not important, and you would be right if you're making a 10, 20 kilohertz audio amp, but if you make something which creates energy up to 500 megahertz, that's wrong. And especially in a DC-DC converter, where you try to make the solution as small as possible, you have parts which are close to each other. So capacitive coupling, E-field coupling with that will have a big part. And so capacitors here, if you open that now, so if they move voltage-wise with their E-fields they have, they will capacitive couple. In addition, if you throw AC currents through any component, and AC currents mostly go also to capacitors, they will create magnetic fields. So you get also magnetic fields from this capacitor and this capacitor, and actually they will couple like a transformer. So you get two windings, and as higher these windings are raised above a ground plane or plane, as higher the transformer type of coupling is. That's also wideband coupling, which easily works to the gigahertz range. Then you get the last coupling mechanism, that you really get electromagnetic radiation if your parts are made in the order of the wavelengths of your frequency, like half wavelengths. The good thing is most times the energy on a DC-DC converter dies down to 500-600 megahertz. So you very seldom get parts which have a good proportion of that wavelengths in that area. So that's normally not the biggest problem. But beware, if you have material which has an high epsilon r, high permittivity, the velocity of light goes with 1 over square root of epsilon r times mu r is 1. Then you can make actually a pretty good radiating unit, much shorter. No? And we just learned there are ceramics out which have an extremely high epsilon R. And there are, for example, 2.4 gigahertz antennas, Wi-Fi antennas made out of ceramic substrate. And that's actually what they use. Now, with these high dielectric constant, they can shrink the original 10 centimeter antenna they would use to a few millimeters and get still a very effective antenna, which has pretty good gain compared to sticking. So PCB usually has an epsilon R around 3.8 if you have an FR4 substrate or something around that. So square root 3.8 would be 2, so you reduce your wavelengths in half. So usually it's on a DC to DC converter not a big problem if you don't make something deeply wrong. Keep in mind that it's also possible. Really, you get an electromagnetic antenna which radiates electric and magnetic and gets electromagnetic waves. That sounds scary, but there's hope because on a DC converter, not all effects are relevant in all components at the same time. So I will abbreviate this today to the most dominant effects, and that's for non-isolated DC to DC converters. Otherwise, times. Okay, now this is through. Okay, now so one of the bigger problems is magnetic coupling of or transformer coupling of capacitors. Capacitors that wise because they are low impedance for high frequencies, so they will create current. Resistors in a fence will do the same, but most times they have resistance way over 50 ohm what you use. So you don't get much AC current, RF AC current. Okay. Keep in mind, electrical fields are created by RF or AC voltages. Magnetic fields are created by currents. And currents flow always in closed circles, so they never end at the ground plane. And with some miracle, they go down to the input. They really flow under the top trace back. So look always for the closed loop. Because that will be your magnetic radiator, your magnetic antenna. So hunt for the full circle. If for some reason you need to decouple with the capacitor on the back side, I not recommend doing that, but if you have to, use a lot of vias to get the lowest inductance at 400 picoamp. In this case, this guy here has 2.8 nanohenry, which high frequency would be quite useless. But in general, try not to make decoupling capacitors on the other side for several reasons. One is the reason that you add a lot of inductance, and the other reason is that you move a lot of EMI energy on the other side. Okay, so avoid switching sides for decoupling capacitors. Avoid using any traces at all. Use massive layer fill. A lot of cases I see that they use thermal traps that they do not tombstone. However, these thermal traps add also a little bit inductance. And the reason that they use thermal traps is that if you do IR reflow or vapor phase, if you do not completely get both sides of a part to the same temperature where the solder gets fluid, now the part could lift up, and it's called tombstoning. And in most cases, if you make a little bit careful design also with large areas, you can make it. You can assure that they increase in temperature at the same time. You don't get tombstone. So avoid thermal traps for critical capacitors. There are lots of capacitors that don't throw much RF current through, so thermal traps are fine with them, but not for the critical coupling capacities. Okay, magnetic coupling. Just to get you an idea, I use an 4430 again, so it's a 3640 volt ups max 3.6 amp, 3.5 amp 250 kilohertz up to 2.5 megahertz step down regulator, which is very successful in the automotive industry. I just took a demo board we have for that and modified it a little bit. So I removed the second symmetric decoupling capacitor here. And I also removed the inductor from the top side. I drilled 2 holes in it and put actually the inductor on twisted yellow wires on the back side, so that I get the electric and magnetic field of the inductor completely out of the picture. And the inductor is pretty much the only one now which you can hook up on wires because it has inductance anyway. It has 10 microhenry, so if you add 300 nanohenry, 500 nanohenry with wires, who cares? The circuit doesn't care. That's the way that you also can hook your current clamp on it now without changing the circuit behavior. So I wind up with it circuit. That actually is the PCBs. There's a 4-layer board, top PCB, where all the current flows. Then we have a solid ground plane on the first layer, second layer. There are some auxiliary signals like enable and signal for demo board. And the bottom is also solid ground, and the EMI filters on the bottom side. Top side, I increase a little bit here, that you see that here's actually the input decoupling capacitor. That's the second one I removed. That's a 100 nanofarad decoupling capacitor. That's the VE trace. That's actually the ground here. And here we have the inductor output voltage, and the L3 is and 2 output capacitors. That isn't actually the latest perfect layout, but I show it here for a good reason, and probe sensing. So that's the schematic. You've seen the 4430 again. Also here's the input capacitors, inductor, output capacitors, and that's the EMI filter. We use a 4th order 2 inductor filter now with 2 inductors in output capacitor here. And in order to show you what an additional ceramic capacitor would pick up for on voltages, I made a probe actually out of an 0805 1 microfarad capacitor. So I took a 50 ohm coax cable, soldered the capacitor, and I have here a flat copper foil which makes a return pass. In a sense, it's a magnetic pickup. However, I want to show now what your capacitor will actually pick up if you use that. And so I use this PCB board. Now I move these pickup around and probe these things. That's input capacitor, output capacitor, and other have an idea. Here. Okay. So first I show with the spectrum analyzer frequency range from 150 kilohertz up to 30 megahertz. And I move up the output current here. Oh, that works so nice. It's good. Not up to 2 amp. And you see now that the spurs here for the coupling for the coupled capacitor come up with current. That's, by the way, input voltage, input current, output voltage, output current. That's the total loss here on that part. And if I go further away with my input capacitor, you see now that actually the induced voltage on my second probe capacitor drops. So it depends pretty much on the position of probably the hot loop and this input capacitor and where I place this capacitor. I go back, goes up again. But in that area, there isn't really a real quiet spot. That's only up to 30 megahertz. So I put it to the output capacitor, or near the output capacitor. You could see there's a little bit, not too bad. Now you can see the current now which goes down in the inductor with frequency. Now the triangular currents will go down, the harmonics will go down with the square of the harmonic number. Go a little bit closer to the hot loop here, there's more. If you actually put your capacitor now about 90 degrees, there will be much less coupling. So if you really go closer. But that's also a trick now if you want to have 2 capacitors and you don't want to have the one talk to the next. put them in 90 degrees. So that is one method. Same thing now up to 300 megahertz. So from 150 kilohertz to 300 megahertz. Now we have 120 kilohertz resolution bandwidth, so it has a little bit more delay. Now you see that up to 300 megahertz, you easily get a lot of energy here on the output. Now is weird. Now even in that range of 100 to 300 megahertz, 200 megahertz, there's still some current as well. So we'll go later. I think we are closer to the hot loop, some more. Turn it 90 degrees, no? That's much less. Go here to some output traces. At certain points. Okay. So why is the magnetic field at the input capacitor so high and so wide band? So again, we know these are triangular currents. They decay with a square of the harmonic number. Here we got the rectangular currents, which are directly. So we have the IDT loop here, and that's what's most is radiating. You can assume about the radiating power that forms a magnetic dipole. And the strength, the field strength of a magnetic dipole will be determined by the current, that's 2 amps in our case, and the area. On the current, most times you can't do anything because the opposite you need a 2 amp power supply, so you can't argue that. The only parameter you have is try to make the area, the loop area, this current turns the cycle around, small. That's the only way to get you, or one way to get you an effective dipole, magnetic dipole RF radiating down in power. And so the radiation goes up proportional to area. Okay. Again, harmonics of a rectangular go only down with n. So they form a first order low pass. Actually, the coupling will be made by dB dt, so magnetic differential over time. So with the rectangular first order low pass and the dB dt first order high pass, you get essentially a flat response. Like you get in a transformer. Okay. High frequency current density. Now we look into a trace and cut the PC board directly in half and look into the phase of a cut trace. If we have high frequency RF current going through it, then you see, as you can see, the trace goes further. Actually, the skin effect will displace the inner current to the outside. That's called skin effect. So current which goes in a conductor in the same direction will always move to the outside, because the conductor tries to minimize any magnetic fields inside of a conductor. Now that's called skin effect. So they find internal magnetic fields. That you don't have much current density internal to a conductor. You can put it even further and say, okay, I get a superconductor, which has 0 DC impedance. Actually gets the same effect or similar effect, but to a quantum area, and you get an high current density only at the outside in the depths, which is called London depths, which is the range maybe of 20 to 500 nanometers. So even on DC with a superconductor, you have this skin effect. So currents are forced outside to the boundary of the skin. Okay. Here I've put the skin effect. Here the frequency is log scale, 1 gigahertz, 1 megahertz. You could find on a half-ounce copper trace, that around 16 megahertz probably. There will be the skin depth. So you can assume that above 16 megahertz, you start get these displacement effects.
Take a break in
Yeah,
the next 5-10 minutes.
Awesome. Yeah, I think now we take a 10-minute break.
Now it's good. Okay.
Yeah, it's a good time, no problem. Okay, so if we click now the okay, so let's continue with the skin effect. So the copper of maybe a half ounce copper will have an skin frequency where the skin effect becomes effective above 60 megahertz. For example, if you go to ferrite material like mu metal, the skin depth of that material is way lower. So even on an say 10 micrometer thick mu material, the skin depth will only go in the range of 10-20 kilohertz. That's the reason that these mu metal, the high mu R material, also shields audio frequencies that good. If you see now, that's for copper, that's for aluminum, that's for tin, and that's actually for high-doped silicon, now which is of no concern. You could actually also show the skin effect of a superconductor, and that is not frequency dependent. It really goes and looks flat here, depending on the type of superconductor, and has a depth of 10 to 500 nanometers. So even on DC, a superconductor will make sure that you only have current density to the outside. I don't think that we have this stuff here soon. I think definitely for these DC converters would help a lot if you have superconducting conductors. Let's see. Okay. If we further look into planes, and now we have a two-layer board where we have an top trace where the current goes in, and the return current comes in the ground plane or bottom layer, and the same way that current which go in the same direction into a conductor make forces that they move out, currents which go in opposite direction will actually attract. So will attract the current density in the ground plane, so most of the return current will be directly under the top conductor, and also the current density will be higher on the bottom side, where they really have the nearest distance. There's sometimes some a little bit to the outside, but most will be on the bottom side. But actually the same as I said now, if you have a ground fault in a 60 hertz high power line. So if the ground return current doesn't go the straight to the transformer, it will follow the complete track under the top line, under the high voltage post, and go directly in this direction. Okay. If you have several traces and they are separated by a solid plane, or like a ground plane where the return currents flow, actually even in the plane in between, these return currents are isolated from each other at high frequency. If that wouldn't be the case, nobody in this room would be able to boot his notebook computer. That wouldn't work because they run on the memory system in the gigahertz range. So you will see the same effect, that they pretty much separate each other. If you want to go into more detail, look at papers about RF microstrip lines, and so you can calculate impedances. There's actually, for this year, a closed loop expression for a very long conductor where you can actually calculate the current density on top here. So I think 1990 or some paper out that you could calculate it. Other than that, you always could use a simulator, field simulator. But for us, if you make a layout, it's important to have a picture in your head, a model, how it works generally. Nobody cares if it's really stops here or here or here, no? But if you know now that the return currents are under the top current, that's usually close. So on a DC to DC converter, most times we have actually the current flowing in the top loop. No? So we have maybe the decoupling capacitor here, and one trace flows to the top switch and goes back from the bottom switches. No? So we get a round loop on the top side, which creates a magnetic dipole. And if you put a solid plane under it, first of all, these current flowing in opposite direction will create eddy current, which are opposite direction. That creates a magnetic dipole, which is opposite to the original one. So you get a lot of cancellation effect. Now, if you put under a top current loop and plane where an eddy current flows. And as you can assume, the distance between those top traces and bottom traces will mainly determine how good these cancellation from these magnetic dipoles is. And so as closer these planes are together, as better is the cancellation effect you get. That's also the reality what you get in a multi-layer board. So we'll later see how drastic that is. To show this effect, I have made a small film of an test now where I used an actual induction stove which runs at 22 kilohertz. I have an omega-shaped loop which picks up the induced magnetic field in order that the induction stove operates. I have to put a water-filled pot. I have to isolate it, and I do not short circuit that loop with the iron pot on it. And I have a magnetic rectangular 10 centimeter squared loop. And the AC current in the 22 kilohertz range is roughly around 100 amps. So it gets quite hot. I put actually a normal household aluminum foil on it, and it flies if I start it. And if I put a solid conductor, a copper conductor with 1 millimeter diameter, as closer the conductor is under it, as better the cancellation is, has less magnetic field the top aluminum foil sees. And even if I go from the top side with my with a eddy current conducted plane, now the flying height will be lower because I reduce the net magnetic field these aluminum foil sees. So that's the same effect you get if you're having shielding planes, eddy current shielding planes in your PC board stack. Okay, so the eddy current cancels the original magnetic field excitation, and as close as the conducting plane is to the original excitation, the loop, as better as the cancellation goes. It also means if you turn it to PC board parts, lower profile components, so flat, short, and wide, are better than higher components because the effect of a plane you put under it, which carries eddy current, is better if you have less distance to these eddy current conducting planes. So a solid ground plane without gaps and holes under and near the excitation field is will work best. In addition, still the skin effect, even so we have a large eddy current conducting plane, skin effect will still look now that the current density will be forced to the outside. And so even at these edges, you have still some current density. So it's not zero, there's some current density. And if you look actually on our 4430 board, you will see that even this is ground, that's also ground. So we got often asked, okay, why do you separate? Why do you make cuts in these? Now you could, it's the same potential, just float it. The reality is that on the return current path here in ground, the highest current will flow directly here from the capacitor on the edges, of these VIN trays and will flow back here on the edge into the capacitor. But there is still some proportion which will be forced to the outside here and flow here to the IC. Same around. And so these areas are not absolutely quiet. And if you just connect them, you will get a smaller current, but to the outside of your board. And that's something you normally like to avoid, is that at the outside edges of your board, you still have some RF currents flowing, because it will create pretty good working magnetic antenna. So there are designs I've seen where they actually put on the outside a small strip and nailed it down. That's still the outside current flowing here at some planes under it, where with eddy current shielding or eddy current cancellation, you could get rid of them. But we figured that if you really have to make a very low noise design, the high currents you can reduce if you cut here in the ground, and make sure that the outside currents are localized, and still have in the second layer a solid plane under it where the eddy current will create cancellations of these magnetic fields. Okay, vias. Vias, if you have to go from one side to the other, are still normal wires, and the inductance of any wire is just the current flowing it, and the magnetic field which is created by this current from zero or the surface to infinity will determine its inductance. A typical 1.6 millimeter PC board stacked via will have around 1 nanohenry inductance, a rough figure. What can you do to reduce the inductance of a via? One has an idea. Okay, you can use more. So parallel them like resistors, who will be 500 picohenry for 250 and so on. One thing. Second thing is you could make them thicker, because if you make them thicker, there's pretty much no current flowing in the inside of that block. So the RF current will flow on the outside of that tube. And if you make it thicker, you can think inductance is current or magnetic field from the surface to infinity. I still get the same field, but if I make it thicker, the field which normally would be here inside is gone. So if I make it thicker, I get less magnetic fields and less inductance with it. If you are an RF guy, you might have to make 50 ohm vias, which have a certain thickness in FR4 substrate. I don't know, it's out of my head. Something of 0.5 millimeters, so it's 1 millimeter, so thicker than the normal via. You could also parallel some standard vias to that. But that's not the worst thing now that the magnetic field creates inductance. That's something, okay, that happens. What's really worse is that if I make vias, I put actually holes in eddy current carrying planes around, ground planes, for example. And with holes, these eddy currents have to detour. So they have to detour, the cancellation effect will be less effective. So it's worse than it makes holes. And to get an idea how these eddy currents look like, I took the original rectangular loop and threw in a single layer PCB board on it and looked on the PCB board with a thermal camera, and actually the eddy currents in that PC board will increase locally the temperature, and with the temperature rise, you can see actually the eddy currents flow. Here you can see the original sides of the rectangular loop. So you can really by experiment show that the eddy currents will flow on the original conductor, even at the low frequency of say 22 kilohertz. As higher the frequency, as more pronounced the effect is, because the attraction current forces will be higher. If you then make in that loop a via block which is close to each other, that there's no copper in between, the eddy currents have to detour. So you can assume that the cancellation of that eddy current going here with these two detours will be worse. Same if I make a straight cut, get a high current density over here, or if I have an closed via block of 4 vias, I still have to make it into. It better works via block of 4 vias, but they are displaced wide enough that there is still some copper in between. You see that here it gets a very high current density because there's only a bit copper, but the original shape is still there. So this shape will better cancel out now because it's close to the original shape than these or this. So if you have a ground plane as a second layer under your top trace, it looks like this. Where are the areas? What's the non-optimum thing here? Can anybody see that? Here, yeah. So you can see there's a lot of slots now, which actually make a cut, which means now there can't any currents flowing here in these circles. Now they have to detour. There are areas on the board where you don't have much topside AC currents, where you can get away with these things. But if you make it under a hot loop on the top side, you will create a lot of detouring currents, so the cancellation is worse. So keep the plane clean. So we learned that there are a lot of worse things about vias, but there are actually also good ones. So if you have a via which is terminated to ground in the next layer, you don't have a complete hole in it. Right? There's a hole in the middle, but that doesn't carry any current at all, so that's not a problem. So if you have a grounded via, first of all, it's shorter. It's only the length of the dielectric distance. And in addition, it does not cut here into your plane. So it keeps the eddy current capability intact. So if you have ground vias, they are actually acceptable even in easy hot. No problem with that. Okay. To quantize this, I made actually a simulation where I took a 4 millimeter apart 2 wire loop, going against each other, 1 amp in this direction, 1 amp in this direction. I cut that thing and made a simulation and put a magnetic pickup here in this 45 degrees direction and recalculated that I got a coupling to 0 dB. So I adjusted the gain in a way that I have 0 dB coupling between these 2 wires and these that magnetic pickup. If I actually bring a plane to 2 millimeter distance to these 4 millimeter apart wires, at the same position, I get already a damping, but these magnetic pickup of minus 11.3 dB. If I bring the ground plane closer to 0.2 millimeter, which would be typical for a 4-layer board, I got a damping of 30.4 dB. So compared to a single-layer board, now there's no plane at all. And that's for magnetic field here in the middle of the air. Gets even better if I place the pickup in an area where typically the next components would be located, which are on the PC board. And I still calculate it to 0 dB, and I get a damping if I have a distance of 2 millimeter of 46.4 dB, or at 0.2 millimeters, 4-layer board, for example, of 86.3 dB. So you get an enormous damping out of a ground plane which is close to your creating forces, and you also damp the magnetic sensor. So that's how planes work in PC boards. You can think of it if you have a switch mode IC, decoupling capacitor, so in the hot loop, the magnetic fields will go around at a certain point as they can couple magnetically in every filter component and so on. Okay. It works so good because if you have 2 magnetic excitations, one transmits and one receives, the ground plane you bring into it will work for both. So passive components, like any traces, capacitors, or whatever, will have the same magnetic and electric transmitting behavior as they have receiving behavior. So it's called they are reciprocal, which means the damping effect on transmission is also effective on reception, and that's the reason that we get these 86 dB of, say, attenuation compared to a single layer board. So the ground plane eddy currents attenuates the emitter as well as the receiver. So in general, it's an aspect ratio game. It's only a question because the field lines will be determined only by the aspect ratio of the two of the transmitter and the receiver and the ground plane. So if you blow it up or shrink it even to IC level, the magnetic field shape will still look the same, and you get the same coupling effects. I took a lot of inductors and used the same DC to DC converter with the same input voltage and load current and output voltage, and just threw different inductors into a G-temp cell and measured what the reception of the G-temp cell or the emission of these parts in the G-temp cell was. And I ordered them in direction of lower radiation. So what does it tell you? Larger is probably not good. You can see here an open mushroom inductor is almost as worse as these large inductor, and as small as inductors goes, usually as better they are. Or we might have an idea why that's the case. Yeah, sure.
Is there a difference between, I see all of them are shielded ones?
Yeah, no, that's not shielded. That's an open one. That are shielded. No, that's essentially shielded. And that's also, I mean, that's an E-type core. But shielded means usually magnetically shielded, which will work fine for the triangular currents. But there's also later in this discussion another effect which will actually dominate the high frequency behavior of inductors. So, hold your question, I answer it as a detail. And just as an idea, smaller is better if you can do it. So sometimes you can't do if the boss tells you, okay, I have to make an 100 amp supply, those won't cut it. You have to go into the direction. That's clear. But it's also clear for an 100 amp supply, the bad thing or the problem in automotive is you get for any unit from the OEMs emission limits, conductive and radiated. And they won't change, and they don't care if you make a 100 milliamp supply or a 100 amp supply. So with a 100 amp supply, you have to meet the same specs. This means you start up with much larger components, much higher components. It's a much tougher job. So that's also the reason, for example, if you open up an EV, an electric vehicle, you will see that the motor, the inverter, the wire harness, and the battery is completely shielded. Because otherwise they wouldn't have a chance. So because you're running 200 amps, I mean, sure, on the motor you have maybe IGBTs which don't switch lightning fast, but it's still microsecond switching with 300-400 volts and 100 amps. So I mean, they got a lot of fun there. Okay. Now let's get a little bit to layout analysis and hints to that. If you make an PC layer stack for, say, medium current up to 3-4 amps, you use your top traces, you get a solid ground plane under it. You might cut into the ground plane into a noisy area and a quiet area. Could also be solid. And then you have a reference ground plane and the bottom ground plane your route union high filters on. So that's it. If you go to much higher power, like 10 amps and more, usually even the bottom plane won't be quiet enough, because even so you have a lot of ground vias, there will be currents here which create voltage differences, and you move these voltage differences to your bottom plane and still have some currents going on the bottom plane. You can see that with magnetic probes. So in order to make on the bottom layer a quiet plane, you just connect this quiet ground plane only on a quiet spot on top, where not much currents flowing. You move it out and you define a quiet spot. That's sort of star node technology moved into a PCB layer stack, if you think about that. And you use a quiet node and make your bottom line, bottom trace, and quiet trace. Okay, so if you make a layout for low EMI, first identify the type of the switcher, so it's non-isolated, and then look for the hot loop. Now we go to layout inside. For isolated DC-DC, I will shortly go into it, but not in too much detail. So first, identify the switcher topology. Now we have seen the hot loops. Now we can identify them on buck, boost, CPIC, tube, for switch, and I have said I went through that already. So if you, for example, have the buck hot loop, there could be a synchronous buck like 4430 or a non-synchronous with only the top switch and a freewheeling diode in it. If you have such a situation, I will later show you a picture. Try to make the inner area of the hot loop as small as possible and place solid ground without cuts under it. So we'll discuss it now. And also try, if you want to make it low EMI, to make the dielectric from the top to the next ground layer or eddy current carrying layer as thin as possible. Normally, you would get, I think, a 250 micrometer dielectric over 1.6 millimeter. But you can ask a PC board manufacturer to cut that down to 75. So if you have a layout which is multi-layer, 4-layer, 6-layer, which is on EMI, same margin, you just need a few dBs more, just ask a PC board manufacturer if you can move the ground plane closer to the top. That in a lot of cases already does it. Use the lowest profile decoupling capacitors, because as a first order estimate, you can assume as higher you rise, the magnetic, the current in the middle of that capacitor above the ground plane, as more it radiates. So again, aspect ratio. So place hot loop on its driver stage as far as away from the EMI filter and the input lines. So you get a lot of coupling directly from the hot loop and other components into cable and into the EMI filters. It's usually the biggest or bigger problem on cables. A lot of cases, the magnetic coupling will be dominant there. And so for that reason, for example, for the typical demo board, we put here, you can move it around. We have the EMI filter here on the next side. You can give it around because that's the quietest spot now we have. If the spacing is too tight, now maybe you have to develop a front camera. Now there's no way, there's only a few millimeters, cubic millimeters, and you have to get your stuff in. Then you have to refrain to some sort of shielding. So you have to separate with some sort of shielding the EMI filter input line from the switcher. It sometimes can be very good done with flex layer, using two plates with flex layer and make a ground on top of that hot loop from the switcher. So that's quite nice. Also, you could use on larger design heat-sink and shielding. I will get later to details on something. What you shouldn't do is, if you have input decoupling with 4 capacitors very close to the part, a lot of cases you think, okay, more helps more. No? So old, we call it in Germany Bauernregel. No? So if farmers go, farmers rule. No? So much helps much. But in EMI, sometimes if you make more capacity, stuff gets worse. No? So what you shouldn't do is, if you have here input decoupling and make an EMI filter, that from here you go into a capacitor on your EMI filter. Why? Because you get a lot of ripple current here, and you would share that ripple current with the ceramic capacitor, which could be also 10 microfarad here, and you get now a ripple current carrying capacitor near your EMI filter. And this current will transmit to all your components and make the effect of the EMI filter pretty much worthless. That's mainly the reason. I mean, if you make a spice simulation of an EMI filter and figure out, okay, at 100 megahertz, I would expect 120 dB attenuation. If you measure that, now if you're lucky, you get 20 or 30, because you get so much magnetic coupling and electrical coupling. And so keep your EMI filter clean, and the first element from the EMI filter looking into your DC-DC should be inductive. Ferrite bead, some inductor, something. Don't draw the ripple current out into your EMI. Use a multi-layer board. We discussed that, because that's much better. And also use small capacitors directly at the output terminal, like 4 or 2s, because even at the output there's some energy left. We saw that with our magnetic probing. That's still in the output capacitors. A lot of high frequency current left up to 300 megahertz. So that creates typically the problem in the FM range. And that's even so a big deal if you have with your output of your DC-DC converter to go off board, like in an LED supply. If your LED string is outside of the PC board, then you have definitely to filter that, because that string will be an antenna, and with this energy, you still would exit it. And if your layer stack allows, it might make a quiet ground layer. Okay. Should always start with the best PCB stack you can think about, so the best layout, and from that make compromises. If you have a really poor layout, so you see it from a glance that's totally rotten, there are no planes on the ROM or cuts in planes, loops, hot loop is large and radiates, don't try to fix it. It's wasted time. So you can throw copper foils on it, capacitors here, filters there, completely shielding that. You keep running in circle, throw it away and make a new, clean, decent layout and start there. That saves you a lot of time. But in a lot of cases, with my customers I tell them, okay, especially if they are a little bit new to the automotive EMI DC-DC, just buy me 2 cups of coffee. I sit with your layouter for 2 hours and make sure that the placement and routing of the critical component is right. I don't care how the rest of the system looks like. Now, just the DC-DC converter and the EMI filter that's placed right. And in a lot of cases, especially the layouters, which are not necessarily RF engineers, but they are computer experts, they are pretty happy if you tell them why they have to do it and move stuff. And you always, if you make a layout, you have to make a lot of compromises. And you need to know, okay, what's the really most important thing, and where are the traces where I can make compromises, which can I move out now, and so on. It's really bad if you have a very dense layout already done, all nodes are connected right, but it's lousy. You have to start all over again. And you tell them the layout, okay, you have to move this here. I mean, he starts yelling and trying. But if very early in the process, you sit there and say, okay, make it right, and good layout doesn't take more area than a poor one. Just to the opposite. And just you have to throw a little bit of your brain material into it. Right? I mean, the field application engineers of MPS are happy to support you as long as it's an MPS regulator. So,
in our case, we have wireless chargers.
Okay. Yeah.
So you have a top line of coils that's emitting RF every now and then, and you add the seen on top of it.
Yeah.
So all that you can take care of in the PCB, you still have emissions onto it. How do you do this?
Yeah. If you have a wireless charger, typically 5 to 15 watts wireless chargers that are most times resonant circuits which run in the 100, 110, 120 kilohertz, and some move the frequency into the resonance port, as I'm saying, with fixed frequency, and just jump up the voltage. That's typically an half bridge which goes into the resonant circuit. The tough thing is you have already a large magnetic antenna, which needs to work fine at these resonance frequency, 110 kilohertz. But it should work very poor at higher frequencies. Now, there's a spot, as I think, in long wave at 200 kilohertz, we have a lot of limits to show. So the only chance is to make the Q of your system quite high, that the first resonance circuit has a high Q and gets a good attenuation, and then you have to shield your board. Now make sure that everything which you have under your coil now will be affected. So first you have some solid shielding on. So I would say if you have here your layer stack, so your transmitting coil. Now you might have here some ferrite material with UR couples in through. Here you have your whatever phone or so you want to charge, and also make sure now that the loops are closed this way, and you have some eddy current grounded layer before you place your actually circuitry. I mean, the danger is you make always a short circuit winding, but if you have that open, I mean, if you transmit 5 watts here, and you transmit 500 millivolt in your circuitry, I mean, all sorts of crap happens. No way. So you have to have at least a solid plane, and easiest is check with a magnetic field probe how good that plane is. So you could always take say a test system and use just a single layer PCB and look if your whatever half ounce copper is good enough. Put a magnetic field probe from under it and look what energy is left, what field is left. Now you can all measure that now what you still have. But you won't get away without at least one solid plane under it. Now the downside is it will be a short circuit for the top loop, so it will reduce efficiency. But I mean, that's one of the deaths the engineer has to die, and you can't get everything. So, I mean, can argue, can say, okay, make it superconductive. So that's one. I don't think now that people like to sit in a freezing car, 5 Kelvin. So start with a good PC, and with the poor layout. If you try to fix that. There's no quiet node. So you put some capacitors there, some shielded copper there. You get typically a ballooning effect. So you can easily make in one area the stuff better, but in the other area stuff gets worse. So what you save on this side, now you blow up on the other. So if you have some, say, quiet ground where you can hook stuff up to get your high frequency current into, and can build also shields on, then you can make a decent effect. Use a magnetic field probe also, and probe around the filter. Place ferrite clamp on the input line. If that helps a lot, then most likely E-field radiation, electrical field radiation, will be your problem. We'll show you later why. And place an E-field shield over the inductor now to verify this. It could also be that your load cables radiate. And you have seen that often that people take our demo boards and then make 0.5 meter cables and put some power resistors. I mean, we put so much energy into our input filters, and then the output cable will mostly radiate. What we don't do is we put an additional output filter to the demo board, because normally the voltages we create are used internal. So we make an internal 3.3 volt for the processor, where there is an EMI ripple like nowhere, so it's anyway noisy. But if you have to go off the board, we have to put some additional filters on. Keep that in mind. You can place some ferrite clamps to it, like you do on a normal cable, to get an idea. Could normally what I try is use either pretty small resistors, which get very hot, no? So you can burn your fingers playing around. What also works pretty good is small light bulbs, no? Halogen bulbs or so. They do not radiate much because they have not much area. And place small 0402 caps directly at the output terminals if you go off. Choose and flex inductor. Now place the capacitors on both sides, close the inductor, place pins higher. If the inductor electrical field is a biggest problem, you can try to shield this with anything which is quiet, like pins higher than the inductor on both sides, or you could place actually an aluminum electric capacitor which has a can on the side to take some of the electric field. Or you can put single or several wires over the inductor. Okay, input filter design. We figured that as we already know that smaller components take less magnetic field, or they are better shielded by a ground plane, that a first order input filter works better than a second order. First order means 2 inductor, 2 capacitors. Now I calculate from here, CL. Now here, that's just our DC-DC converter. Don't do a ceramic capacitor here. There was a guy making TV sets in the late 40s and 50s called Munzing. He wasn't, I think, an engineer, but he was famous for running around in his R&D lab just with a cutter, and he cut it out parts until the TV set didn't work anymore. And then we sold it the last one and sold it. Under the engineering society, it's not very popular. If you throw so much energy into it, you make a really decent performing unit, and then your boss comes in and throws most of the good ideas out and says, okay, it's good enough because if I'm close to the main TV tower, it's still working. If you want to know a little bit more about it, there's a nice piece from Bob Pease about Munzing in electronic designs. You can close it up. And that's already a poor practice from an engineering standpoint. However, what you usually do on EMI is worse, because you don't start with a design where you know, okay, it's most likely passes, and then I make it cheaper and simpler, but it's the other way around. Now, a lot of cases, management thinks, okay, EMI is difficult to tell anyway, so don't worry, you just make the functionality and look for EMI later. So if then the project goes through, software is done with delays, then the poor chap in the EMI lab gets this thing. And the reason that he has so much gray hairs is not that he don't get any light from the outside because he's in an anechoic chamber, but he has such a stressful job at the end of the schedule where everybody looks at him again and makes the EMI go. And it's a total nightmare. And he has to figure out that there are major changes need to be made. So make at least a Munzing design where you can cut off and sweep out EMI measures. It doesn't mean that like baby powder, you have to move around Faraday beads everywhere, but make a decent thinking, make a layer stack, ground planes, an EMI filter where you know, okay, there's at least a pretty good chance that it passes EMI. And if it's all done and you see, okay, boy, I get still 10 dB more attenuation than I need to pass EMI, then I can start making compromises, make stuff cheaper. So reduce the layer stack and make compromises. But that's definitely a faster development course than the reverse Munzing design lots of people do today. Will say, okay, now just let's ride our luck and let's see if it passes. So I've been so often through it now that okay, everybody which is long in the industry, it's a lot of stories to tell about that. Okay. There's also some people thinking now that computer-aided solution will work. And actually, I think we are also looking into it. On circuit design with SPICE, since all nodes have a node has no voltage difference, that works out fine. And on an IC design, you don't have any other choice, and because you make a schematic, then you tape it out, and then you wait 3 months until it gets out of fab. Then you can look at it, and even look at it doesn't mean that like on a PCB you can probe every node with a probe or so and cut here and there and add a capacitor. But most times it's very limited what you can do. So if it doesn't work, you're pretty much on your own. Typical, there are revisions from A up to F, and F means usually fire. So there's a lot of pressure to get these stuff out there. So SPICE is a pretty good tool if you can't access the whole thing. On the other hand, if you have a normal PCB with a unit above a handful of megahertz, SPICE doesn't tell you much of the truth. Below that, clearly, so if you have in the fundamental switching frequency and the first few harmonics, the currents and voltages stick to the wires, to the traces. Above that, magnetic coupling and E-field coupling clearly dominates the field. So on a simulation, you would have to get extremely good models about these electric and magnetic field coupling effects. And you can assume if you ever have simulated units with several transformers on SPICE, at a certain point you get a lot of problems there, that simulation gets very slow and so on. In a sense, you would need to have a quantum computer to run it in a decent time. So a really fast computer which does all calculations in parallel to get it out. With my gray hairs, okay, easy. I take a quantum computer I already have. So even the NSA doesn't have a decent one. So I take the PCB and take just electric and magnetic field probes and probe around, because my circuit I have is actually a working real-time quantum computer. It does everything and tells me everything what I need to know. And that's one of the nice thing about the engineering job. The Maxwell's equation, which determine besides the quantum mechanics, pretty much everything, are stable since the first few seconds where the universe was born, about 30.6 billion years ago. So, I mean, they are time invariant, they are PowerPoint invariant, and no matter how loud your boss yells, I mean, that's physics. So that's the one you have to deal with. And I get, if I probe it, the same answer tomorrow as I get it today. And most times, the problem sits in front of the screen instead of the probe circuit. So what the processing power between your ears is usually probably your biggest asset. Now you have to use that. Okay, back to DC-DC converter, simple one. If you have a non-synchronous DC to DC converter with a freewheeling diode and a capacitor, now here's the hot loop. You can also think that essentially the current is switched from here to the diode back and forth, which means if you make a layout, place the input capacitor directly adjacent to the diode. They both look into the switching regulator, which is small slot 23, and here make a small ground plane that they share the same area where the current goes, and here it goes out to the inductor. You could even make a common small ground plane out of it. So I have often seen layouts where they say, okay, now here that's the input decoupling capacitor, and that I set close to the switching regulator, freewheeling diode is over here. Because it's just only a diode. I mean, that's really poor because switching regulator has only a top switch. It doesn't have much ground currents, so how close this is to the ground of the IC doesn't matter much. It has to be very close to the V-in, and this is very close to the switch node, and that's the optimum thing. So it's pretty simple, doesn't take more area, and helps on EMI a lot if you do this thing. Place under the hot loop a solid ground, as you have seen on 4430. At a certain point, you have to make holes in it. No matter what, because V-in has to go through some signals, but make them away from your hot loop, so that the eddy currents can be cancelled out without compromise. Place the EMI filter On the back side, it's actually not a perfect example. I will later probe that. However, with the aluminum capacitor and these input EMI filters on the back side, now you're usually better off. Now let's come to a radiated and conducted EMI test. Conducted is usually a Leeson 20 centimeter cable device under test. Radiated up to 30 megahertz is a monopole. It's a shorted rod antenna, which is hooked. These are all CISPO 25 measurements. We're talking automotive here. On a table, and the table is actually attached to the rear on the cabin, pretty solid, with lots of copper plates, and also the rod antenna is on a solid plate, which is connected to this conductive plate. And the device under test is actually on a 5 centimeter, mostly styrofoam, above this table. And here you have the Leeson small supply source, and the car battery, whatever, and here you have your device under test. Okay. So to show that even real high current power stuff can get through EMI, I used a part which is not yet available from us. I think at the end of the year, hopefully we are ready now. So as I speak, they are hard working on it. And here you see a unit which has a 6 to 7 amp, 6 to 8 amp step down regulator, and twice of them running sub AM in the 460 kilohertz range. The part itself could run from, I think, 350 kilohertz up to 2.5 megahertz if you want to. But at these high powers, it doesn't make much sense to run them at high switching frequency. I'll get later details why. So we have 2 times these 4436 with symmetric input decoupling, output filtering, and a single common EMI filter for both. So that's the circuit. Here are the 2 main inductors. Here the IC. The middle capacitor is shared between these 2. Now it's the outside capacitor. There's an aluminum coupling capacitor. And on the back side, now we got the EMI filter. Efficiency is quite high. So in the 12 amp range, we still are almost 90% here. That's 6 amp each. And here's the total power loss. That's output power minus input power. You can see at 12 amps, we are in the range a little bit over 4 watts, but these 4 watts distribute over 2 ICs and 2 inductors. So that's still pretty manageable. Here's the top layer. Again, input decoupling capacitors. There's the 2 ICs, output inductors, and there's the output decoupling. And what you see is even in the top layer, there's a cut. That's because the eddy currents, the currents of the hot loop, which go on the ground to the outside, should not be at the edge of that board. And I cut also in the inner layers, but what you see is if these cuts don't overlap. You don't want to have a cut going through all layers where you can look through, because the magnetic fields go also through where you look. So make it a little bit like a labyrinth style, so that in the layer stack, you jump back and forth with these things. So that will get a lot of additional attenuation. So the second is pretty much solid ground, also outcut. Third layer is VIN routed here. And here we have these auxiliary, whatever, concept, force continuous mode, and AM mode, and sync in, and these things routed. And the last layer actually is a quiet layer. And if you look here on the normal ground vias, on the last layer, they are cut out. So that the high current stuff, which flows here, is not affecting currents going on the last layer. I only have, outside the cuts, the ground pins around here, a massive via block, which connects the top layer ground to the bottom layer. So that's the main connection, the star ground. I mean, do I have to put it there, or could it be another place? Probably yes, it could be another place. But important is now that you have a sort of defined star ground. At least it should be a quiet spot. Okay, first let's look into monopole measurements. Monopole, I call these radiated measurements from 150 kilohertz to 30 megahertz. So monopole electric field, that's peak. Now you see here I have, that's not CISPO 25 limits, it's actually OEM limits from the German manufacturers. That's, in this case would be BMW, but the VW and Daimler, they all made a common spec, it's called LV50. They have the same limits, and because they figured, okay, it does not make sense if an Tier 1 makes an ECU which only works at, say, Mercedes, Daimler, and VW needs another one. They figured it's much better to run through some common specs if he has some ISO standards already for the typical broadband pulses. Could also put the Ford EMC specs. Ford is so nice to publish the actual EMC specs. I think the latest are 2016. They are looking quite similar, so there's no big difference, drastic difference, what you can see. But what you could see is that on average, the limits are typically lower, most times 10 dB lower. The second harmonic now will just not pass here for that switch. If I use a fixed frequency monopole E field and I don't do anything, that just straight that on. If I use spread spectrum, I get for the second harmonic a decent attenuation, roughly, I would say about 10, 11 dB. I could also theoretically expect. So if I go with that board, goes spread spectrum, and this part is also will be offered as spread spectrum, even that board will pass. But if I just also add a heat sink to the ICs, which is formed in a way, I think I guess heat sink around too, that it goes over the inductors, the monopole is perfect. So, and that's with spread spectrum, and it would still be with fixed frequency, no problem. We'll later see these measurements too.
Christian?
Yeah.
Let's take a break in 5 minutes.
In 5 minutes, okay. So I go through it and then we break. If we go now to radiated measurements, 30 megahertz up to 1 gigahertz, now you see more interesting cloud-based limit lines. I actually combine the quasi-peak and peak limit lines because on a fixed frequency switcher doesn't make any difference at all, and so I don't have to run that much tests. And you can see here on the noise level, or on the noise floor of my measurement system, you can see here there are some gaps where I run the resolution bandwidth from the 120 kilohertz nominal to 9 kilohertz here. There's some areas now, I think it's whatever high frequency police radio or so, where they have a 9 kilohertz specification, the rest is 120 kilohertz. You see that the normal one on peak almost passes, just above the AM band, now with FM band. You can see that there might be some problem. On average, it's a little bit worse because average limits are a lot lower. You can see it's the same thing, but in average, here in the FM range now, there's 4 meter police radio. There's an SRD range, I think, with 9 kilohertz, it's 120 kilohertz. And here actually, they have a resolution that is of 1 megahertz. So if you go between fixed frequency and spread spectrum, you see that spread spectrum helps pretty much up to, say, 200, 300 megahertz. Above that, there's not too much difference. Anybody has an idea why that is? That maybe at 400, 500 megahertz, there's no difference between a fixed frequency and spread spectrum switcher.
They open up the bandwidth when they.
I mean,
do they open up the bandwidth of their receiver when they get up to those higher frequencies?
No, it's all the receiver goes here with 120 kilohertz resolution bandwidth. So the resolution bandwidth of the receiver will except for these small areas where it's 9 kilohertz, will be constant. But the general idea from your side is right. It's really 120 kilohertz resolution bandwidth. And a switching regulator oscillator in an IC isn't an X-style oscillator. It's not crystal clean, I would say. It has some inherent phase noise. And the thing working at 400 kilohertz at 400 megahertz is frequency times 1000, which means that the little bit frequency jitter you have at 400 kilohertz is multiplied by a factor of 1000 at 460 megahertz. So it already makes, with its own phase noise, its spectrum signal. And so you don't have to introduce spectrum. It has it already there. And so keep that in mind that most likely, if you have a problem at 300, 400, 500 megahertz, there will be not much difference if you have a fixed frequency or spread spectrum part, unless you synchronize your part with a crystal oscillator, because then you make really low phase noise spectrum. But a normal running switching regulator will already be spread spectrum due to its phase noise at that high frequency. That's average. And interesting, if I go then and put a top heat sink to it, now that pretty much overall you get an additional maybe up to 10 dB damping. So you are easily passing with a 12 amp supply the EMI spec. Conducted, so it's a 20 centimeter line over Leeson. Fixed frequency, now you see the fence you could expect now, and it's a switching frequency and then all the harmonics going up. Just hairy here in the FM range. If you put spread spectrum, that gives you an additional several dB. And if you put actually a shield over it, it becomes even much better. And that's something which would surprise some people, that conducted, which means I measure really on the input lines here over the wire. It makes a difference if I just make a partial shield over the IC and the inductor. It's because most stuff really is E-field radiating out of the inductor in that area. And even at fixed frequency, with these shield, now you will have a lot of margin. So you don't necessarily need a spread spectrum for it. Sure, spread spectrum helps here, but if you do it right, managing the electrical fields has an higher impact than going between spread spectrum and fixed frequency. But again, we will offer this part in both versions, so that you get a fixed frequency and spread spectrum. So I think that's a pretty good place where we could make a break. And
do you want to summarize, or?
Yeah, I think I later started could do the summarize. So the main coupling effects are capacitive E-field coupling, and we have magnetic transformer coupling, and we have galvanic coupling. And the interesting thing is you don't see here in these frequency plots much frequency dependent or filter types of action. Either you move the whole thing down or up, but you don't see any first or second order filter action, which simply means that the major coupling mechanisms will be capacitive and magnetic. They do not go over your traces, they go over the top of your PC board. And for capacitive or E-field radiating, fast moving nodes with high voltage have to be there. And for magnetic and conductive, the IVT current. Okay, that's no break for.
Can you see that on the
No.
no? Fighting.
No. Now, no, but now we can
See,
see.
that's the two thing. Okay, now then I try to go to the desktop too. Oh, here we go. So for some reason you have to toggle it. Okay, so let's continue. Mal wach machen. Okay. EMI is called black magic. Why? Now because you can locate the main EMI creating capacitors and other components rising above the PEC board level will couple like magnetic transformer windings, and inductors will couple E field. We'll get into details of that one. First of all, we get often the question, does the orientation of the inductor matter? And I just took a 4430 board and XAL, I think 60, 10 microhenry inductor, and measured it average in both orientations. So in one orientation it will pass the limits, but the same board in the other orientation doesn't. And if you look close here on the second harmonic, now it will be probably 5 dB more. So it's a significant difference. If you look conducted, also that's one direction, and the other direction now it will change rather drastically. And in one direction it will pass actually EMI, and the other it don't. If you go radiated from 30 megahertz to 1 gigahertz, one direction here, yeah, sort of passing, and here it's going to fail if I change the orientation of the inductor. Inductor is a two-terminal device. Why can it be the case that it makes so much difference? And just if I turn this thing around 180 degrees. Anybody has an idea? Okay, so let's think of it, how an inductor is built. Yeah, later. First of all, if you make layer stacks, don't line up the holes. Go and make it in a labyrinth cut, because here the magnetic fields you get here will create eddy currents, which cancel that out. Same here, now they cancel it out. Here will be cancelled out in this plane, so you get a lot of cancellation. I don't make sure that you can look through those guys. Let's see here. Why does inductor orientation matter? Come, I think to it. On most EMI measurements, the device test this. That's the right presentation here. This is still 06. Do you see anything?
No, we see your screen.
It's okay. 6, that should be the right one. So the full screen. Okay. 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 common mode currents in inductor and switch node. If you measure an DC-DC converter conductive, you have an PC board which is hooked with 20 centimeter cable to the lesion. It's a typical conducted setup. Typical conducted setup. And if you talk about differential mode currents flow here into the receiver and out common mode current flow in the same direction. If we turn into a DC to DC converter, differential mode current will flow in one wire in one direction and the other wire out. However, those from this side can easily be, say, decoupled with capacitors. So usually differential mode noise on a DC-DC converter in an automotive input environment, 14-volt automotive shouldn't be a problem because they are so easy with capacitors to get to pretty much zero. Another story is common mode current. Common mode current will go parallel on both input lines and go out to whatever path is available. Could be ground path, but sometimes you don't even have a ground path. But in general, for a common mode current, since it goes in the same direction, you can reduce your input wire harness through a single line. The current comes out anywhere here over PE. Sometimes you don't have a common mode, it's common return, and still there's common mode current into a completely free PC board sitting there, like on this conductive test, sitting with a PC board on a wire harness just above a 5 centimeter styrofoam board. Now, so the current definitely has to go anywhere, and so it will go capacity-wise over the board capacity down to the grounded table. So, in a sense, this thing here, demo board with a 20 centimeter cable, looks like an T-loaded antenna, where you have a common mode current here, and you have here a 50 ohm lesion in that direction. Problem is, how can you create AC current here? There's only one chance is by E-field radiation, by electrical field radiation. Because if you have magnetic currents or currents on the surface anywhere here, they will all, because they are round loop, will cancel out. There's no way if a surface current creates a net magnetic field and this goes into that direction as magnetic field and creates then a voltage over that. Only an electric field radiator or a capacitive radiator can do that. So that will be for some surprise. So if you want to create common mode current in a single trunk harness, I'm not talking about if you have lots of wires, and you can go around trip. Now, but if you have only a single wire which ends in a unit and it radiates, it's all electrical field. If you don't have differential mode but only common mode currents, it's electrical field for the input. There's a lot of stuff on cars which has an essential single trunk harness. That would be any LED light, some backlights, interior lights, and stuff of that. So if you don't have a complex cable trunk with lots of wires, but there's one single trunk, and you figure out that there's a common mode current there normally must be an electrical field radiator which creates that current. Now, let's take a measurement. That's actually an electrical field probe, and we measure from 150 kilohertz to 30 megahertz and move that over an operating 4430 DC-DC converter. You see, as long as the E-field probe is above the inductor, the emission is here the highest. If it's off the inductor, in whatever side, then the emission goes down. So I have to really to get off the inductor to get less electrical field. Can play the same experiment. Up to 300 megahertz. Takes a little bit longer because the resolution bandwidth of the spectrum analyzer is now set to 120 kilohertz. But here's the same experiment with up to 300 megahertz, and you can see that there is a bit radiation in the high area, but mainly 0 up to 100 to 150 megahertz range. You have to get off the inductor not to reduce electrical field. So obviously, the highest component in our series converter radiates the most electrical fields, and that's the inductor, which is sort of counterintuitive because any inductor manufacturer thinks, okay, here's a magnetic component. But EMI-wise, it's an E-field contributor or an E-field radiator, at least for the high frequency area. Sure, now if you talk about the fundamentals here, the low frequency, I mean, there's a lot of magnetic energy, but for the high frequency, the energy which comes out of that inductor is mainly electrical field. Okay, so the node with the largest AC swing, which is usually the switch node and everything which is attached to it, would be a boost capacitor and boost resistor and things, and that which has the highest elevation, which is typically the inductor, it's the largest area, it's also the inductor, dominates the radiated E-field emission. What you can do to test that is, if you think, okay, I have a capacitive plate, which will be the top of our inductor, if that's the culprit, I just shield it with an electrical field shield. Electrical field shield could be just a wire mesh or something which doesn't carry much currents, but picks up the electrical field and it goes up. Since it's grounded here, it will only go this way. Won't go much around here. So that's actually the reason that this 12 amp guy, just with a heatsink, is absolutely quiet on monopole measurement because that's an electric field. It operates as an electric field. So you can shield your inductor, but don't forget the switch node areas on the PCB and MOSFETs on ICs. So best is a solid shield 1 millimeter away from the top of the inductor surface because it will otherwise create eddy currents. So RF E-field emitters are typically can be held by electric field. Now, what about magnetic? So I take now a magnetic probe, and that's a probe that's a single loop in that direction. So magnetic field has to go through the surface of that thing, not to create here. And I think I measure here. Yeah. I measure up to 300 megahertz with my magnetic field probe, and I go over the inductor, and I see, okay, sure enough, I get the low frequency content, but what's that? Up to 300 megahertz, I see still a good energy, which is even lower if I go over the hot loop and switch node and close to the input capacitors. But here at the inductor, now stuff here comes up. And now I turn the same probe, same situation, just by 90 degrees. Oh, I'm gone. So what happens? And normally you see an inductor, it's wind up here, now it should be a symmetric field coming out in all directions, but it actually doesn't. You see the decaying triangular waveforms of opposite frequency. not much else. So why is in that direction much more energy than in this direction? In this direction, the magnetic pickup is in this way, which means current goes in that direction through the inductor. Here, current would have to go in this direction through the inductor, not to create a magnetic field. Anybody has an idea why it's such a big difference? No? So that we have high frequency, 200-300 megahertz currents going straight through the inductor. Doesn't care about the winding. Okay, if you think how an inductor is made, you get a switch node, then you have a winding step, and it goes back on. So here we have the output node, here's the switch node. So obviously we have some current which goes through. How can it do it? Because we have an inductor, but the inductor still has some capacitance. So we have here capacitance from each wire to the next, and also as in this case as a molded inductor, these material here are isolated iron powder, small iron powder with isolator outside, but it's essentially as an epsilon r and permittivity, which is not 1, it's a little bit higher than 1. So you get a capacitive path right through the inductor. It doesn't care about the winding. And actually, you can calculate the capacity from these self-resonance frequency. So the inductance, 10 microhenry or whatever is known, 1 over 2 pi square root of C, what we want to know, times L. L is known, so we want to look for C, so that move up, square that, and you get the right equation. And you figure out that C will be in the range typically of 5 picofarad, 7 picofarad, something like that. And it's actually a current which goes right through the inductor, doesn't care about the winding. So that's the reason why the high frequency comes up. So you see still electrical fields coupled through these, current through these capacity going right through the inductor. If you want to filter that, because that's an additional pass here, switch node bounces between 0 and 14 volts, rise times in whatever, a few nanoseconds, if you are lucky. V out is, you see lots of ceramics. So what you have actually, you have a switch node which bounces with 14 volt. You have the C from the inductor, maybe 5 picofarads, and you have the C out, which might be 44 microfarad. So a huge capacitive divider. However, this guy has parasitics, has ESR and ESL. So in the high frequency range, you have to make sure that the impedance pass here should be low somehow. So what can we do? One is use 2 22 microfarad capacitors and putting in a way that ground is the outside, that the magnetics, the current goes in this direction. So the magnetic field, if you're looking from far away, will cancel out. That works usually quite well. However, there's still enough energy that if you would put at this output half a meter cable to an LED, you wouldn't pass EMI because there's still too much voltage. So if you go off board with that thing, you have to filter that. So it's quite simple. What you also can do, rather successful, it's on 4431, that's a 1 amp version of the 4430. Use a very flat inductor and use 2 capacitors. And if the capacitors are symmetric to it, you will get from the outside a lot of cancellation. You have only half the current in each capacitor, and you have cancelling loops. So that works all very well. This board on fixed frequency passes EMI no problem. So because the inductor is so flat and it has such a symmetry. You can buy shielded inductors. That's actually in Vishay HALE series. The shielding works, but it has some drawbacks. First drawback is directly as a plate above the inductor. So it creates, since it's directly on the inductor, a short circuit line. And you see that you can measure the efficiency quite easily because you can remove that shield just with a screwdriver and get rid you lose typically on a 500 kilohertz switch about 2% efficiency due to these shielding. And if it's critical now, that's something you try to avoid. Second thing, which is not optimum, is that on both sides, the especially for the switch node, you have a large area which goes up, which also creates a lot of electrical field. It moves even electrical field around at your high up. You will get a big improvement if you just cut it away. And so you're better off with an inductor which only has connections on the bottom side and maybe some shielding. And I would usually go, if I have to optimize efficiency, instead of a shielded inductor, I would make 1 millimeter above it, whatever PCB, copper with through-hole wires or so on, and shield that electrical field. But make it a little bit above of the magnetic material, you get lots less eddy currents, because if you're directly on the magnetic material, you can think that at the border where you have your eddy current, there will be no magnetic field. No? So you really drive the magnetic field into the material. You have less effective material, and you get more losses. Again, if you have to go off board now, like often with LED supplies, you need to post filter. And for post filter, everything what I set to input filters yet is valid. Then I want to jump to a thing you should also be aware of. I just put a normal demo board and hooked a totally non-connected coil, which has, I think, a 22 nanofarad capacitor, and make a resonance circuit. But it's free, so you could remove that, throw that around, and so you just the pins, that's the EMI and ground pin, and just put it over the pins. And what you can see, that it is a resonance of 57.5 megahertz. It puts it up. And here's a blue one is a situation without, and that's with one. Why is that the case? Now you have a totally unconnected resonance circuit, you put it in, and all of a sudden it creates currents somehow and radiation. Now, how does it work? And I made the test. I took the same loop and removed the capacitor, and you see it's flat. It's a resonant, and it creates a problem. Problems with resonances is an LC resonance goes through a complete 180 degrees phase shift. So whatever a resonance circuit you have, if it has an high Q, it will actually create a pretty perfect matching circuit at one certain frequency, where it creates a perfect match about your source and your sink. So be aware that you create any high Q filter components or say strip lines, which creates like antennas. It's also pretty typical if you measure these high Q circuits, which aren't crystal clean. Crystal is simple now because it has a very low phase noise. You can see that with the harmonics. But if you have such a thing which is a little bit wider but has a relatively high Q, it might be a resonant created on your circuit. And a resonant actually matches impedances. Now, there's always one point now where you get on a resonance circuit a perfect match from the inputs on. Just that you have seen that. Okay, that's actually the frequency content of a switching regulator. Switching regulator is pretty ignorant about certain frequency. So essentially it's a comp generator with switching frequencies and all these multiples and goes down here. I have here 1 gigahertz, it's 300 megahertz, so 400 or 500 megahertz, and then stuff dies down. So that's typically it's a comp generator, wideband. So there's nothing which tells you, okay, here I make a lot of noise here in the FM band or whatever. No, it's wideband created. So you have to also filter a wideband. Switching frequency and EMI. We figured now that the switching regulator is a comp generator essentially. And if you, for example, have a 500 kilohertz switching regulator, we'll have every 500 kilohertz such an area where energy is, no? pretty much flat. If you now take the same switching regulator, everything else same, input voltage, output voltage, current, inductors, everything set. Only we jack up the frequency and double it. What happens? With doubling the frequency, we get double the edges or double the energy, no? Double the edge energy, double the energy here inside of these comms. And that gives 3 dB more EMI, now because power, now we're talking energy or power, it's 10 times log of 2. But these double energy, now instead of having every 500 kilohertz a bin to wander around, it says only every 1 megahertz a bin. So due to the fact that I only have now half the bins for the same energy, I get an additional doubling. So doubling the switching frequency increases the EMI by 6 dB on fixed frequency switcher. I get some questions about that, and late night I stood up. Okay, first let's look here. If you have from 1x, 4x the switching frequency, we get 12 dB more EMI on a fixed frequency switcher. Okay. In order to test that, and for other purposes, I actually built a comp generator. I didn't use a switching generator. Could use a switching generator, but I needed some test circuit to test EMI equipment. And for that, you make a comp generator. Comp is actually a fence in the frequency, what we have seen. And if anybody has had some idea about signal theory, comp in frequency, if you Fourier transform it, then you get a comp in time domain. Comp in time domain is just pulses in time domain. Yeah? So in order to make a comp generator, you have to make a pulse generator with very short pulses. And the repetition frequency of the pulses will give you direct the repetition frequency of the frequency comp increases. Okay, so to do that, I used a Peckel D flip-flop. It's actually an idea from two guys here, Yopi and Muhammad Sundrati, and they were in Pakistan. But they're quite clever because these Peckel parts you can buy from Motorola for whatever, $8 or $7 in DigiKey. And they work quite well. It's actually a D flip-flop. You use a normal oscillator. I didn't use that here, these simple boards I used in direct inside. But if you drive a D flip-flop, it just sets, and with the delay line, it resets itself. And that's actually the layout I made to it. And here you can see the small Peckel and also some little 9-volt battery and so on. I actually had to go to a customer of mine which had a real scope, which is a 20 gigahertz LaCroix to check through the pulses I get. And I got a pulse length of about 400 picoseconds with rise at fall times of around 200 picoseconds. So quite fast, much faster than typically in switching regulators. So you can assume I take these pulse, this pulse which goes negative, doesn't make any difference to a positive pulse, and repeat it just by my normal crystal oscillator. And that's the frequency response if I get, I set a 10 megahertz pulse generator. So I get here in the low areas, actually from 0 hertz to 1 gigahertz, and that's 1 dB per division. Normally would you say 10 dB per division, but it's pretty flat comp generator, so quite good. So at 10 megahertz, we have a reference, a typical level at 65 dB here. And I can just flip a switch and change the frequency just with an old TTL divider. And if I have only 1 megahertz switching frequency, it's at 55 dB. So from 65, by dividing 10 frequency by factor of 10, now we go to 55 dB. I can further flip a switch and go to 500 kilohertz, and then I get 39 dB. So from 500 kilohertz to megahertz, I get the 6 dB. From megahertz to 10 megahertz, I get 20 dB. And the same for switching regulated. A lot of our switching regulators, like 4430 and 4436, they have an RT resistor. You could also, just with an RT resistor, run the same experiment and then
change the frequency. So on a fixed frequency switcher, doubling this frequency makes the EMI 6 dB worse.
So why do people want to run at higher frequencies?
Because, yeah, at a certain point, you get smaller inductors. And if you are on a point of load system, so behind the first switch in automotive system, so if I have an, say, 14 volt in and makes me a main 5 or main 3.3 volt, and then I have a POL system, I'm not that sensitive anymore to EMI. So first of all, I have lower voltages at 3.3 volt. I can easily switch with 2-3 megahertz because the jump is only 5 or 3.3 volt, and I can use relatively small inductors there for these POL parts. And they are not that sensitive because I have my whole big input switcher in front of it, which pretty much shields that. And I have a big micro, which also creates a lot of noise in whatever sealed environment. But if you go to the front end, and I would say if you are in the range of, say, 500 milliamp, 1 amp and above, most times the little bit smaller inductor you get with 2 megahertz compared to just sub AM isn't worth it. I mean, I have customers asking me, okay, I want to be clean in the AM band. I want to start at 2 megahertz. You can do it, but the efforts and money you throw into EMI filtering and special shielding your DC-DC converter is way higher than what you simply save on an, say, an inductor which is one size step smaller. And so it's a trade-off. I mean, you can always go higher in switching frequency, but you have to know now, okay, you make your EMI much worse, and you create yourself more problems, and you have to throw then money into shielding and other effects. And here I think the 4430, the board is around, I don't know, you have it here. I mean, you can use the same board and run it at 2 megahertz. Now, the inductors get a little bit flatter. You get, instead of 60-60 to 50-30, say L. Efficiency drops, because you're switching fast, you got more AC losses. If you really go from 14 volt down to 3.3 at higher currents, currently I would say in most cases it isn't worth it unless you have a certain requirement that you have an RF AM receiver which needs to be absolutely clean. A lot of, I had cases for an AM receiver where they actually synchronize the switching regulator and switch the synchronization frequency depending on the AM range they are into. So that's something which is done. I mean, at the end of the day, the engineer tries to get to the cheapest hole now, which does the job, now, which passes EMI. And in a lot of cases, especially if you're on higher current, it doesn't make sense then to go to that high frequency because you start getting into an EMI now. You can manage it, but you wonder how much effort you throw in. I mean, at the end of the day, you can always make a perfect, complete shield over your DC-DC converter, use capacitors, feed-throughs, and build a system which looks like an HP spectrum analyzer from inside. No problem. But in automotive, typically, you don't even have a complete shielded environment. You have a plastic box. And if you start with a plastic box, you make your life a lot harder if you start on the 14 volt side with a 2 megahertz switcher. That's my experience. I mean, that guy easily runs at 2.5 megahertz, no problem. It's not that we have anything which would prevent us from proposing going to 2 megahertz, but we went with several automotive OEMs extensively to it. There's also a 4-phase version out of it where we are looking up to 30 amps output current. And the final conclusion was that, I mean, you are much better off efficiency-wise and EMI-wise if you just stay sub-AM band. You will get some spurs in the middle of the AM band. Either you run spread spectrum or you can shift around if it's a problem. But that was the bottom line for it. So, I mean, nobody want to prevent you from going to 2 megahertz. I wonder there are people which like to use GaN FETs and go 10 megahertz and more. Easy, no? But physics still applies, no? So they will have some fun in the effort. Maybe you're going above 110 megahertz or something. Yeah. Yeah.
theoretically, I mean, if you are on low voltage, actually, there's an Intel processor core where they have the core supply inside of the processor box. And I think they run it in the range of 180 megahertz. It is only 70% efficient, but since they have a big heat sink and nobody cares, and they create these power very close to it. So there might always be reasons that you say, okay, I go really ultra high frequency. But if you have to pass these stringent automotive EMI specs, I mean, it's very tough to shield against that, that you get through it. Okay, jump to spectrum. Okay, here's the table. What's the maximum attenuation you can achieve on a perfect spectrum system? The rationale is pretty simple. I mean, a switching regulator will create a comp of its switching frequency, 2, 3, 5, and so on. And in a sense, you take your EMI receiver with its resolution bandwidth and you dial through it, like you dial a receiver up and move it through it. So what you do, in effect, is you actually convolute the spurs with the bandwidth of the resolution bandwidth of the EMI receiver. So you widen up these traces essentially by 9 kilohertz up to 30 megahertz, or you widen them up by 120 kilohertz in the 30 megahertz to 1 gigahertz region. And then it's pretty straightforward. That's the area where the EMI receiver will pick up energy, and that's the area where it's deaf. So if you spread your energy evenly, the proportion of the receiving to the deaf area will determine the attenuation you can get. So it's a pretty simple equation. It's 10 times log 10 over resolution bandwidth divided by switching frequency. So it's fairly straightforward. Which also means that in the 30 megahertz to 1 gigahertz range, 120 kilohertz resolution bandwidth is much harder to get any decent attenuation. So I put here 400 kilohertz switcher, 2 megahertz switcher. What maximum resolution or attenuation you can get. And that's the maximum if you had a theoretically perfect modulation scheme. If you measure average, you will get close to these numbers because average is so narrow bandwidth, so say making it average, that it comes out. If you measure peak, or peak, most times you get numbers which are below these numbers. But that's straightforward math. Okay. In order to get an idea where your EMI problems might come from, you can use magnetic field probes. Here again, now my 4430 circuit, now with full capacitors. Here's the input voltage, input current, output voltage, output current, and that's the spectrum. Now I think up to 30 megahertz. So if I start that, that's a probe which is only 0.2 millimeter loop, internal amplifier hooked to the spectrum analyzer, and you can actually magnetically pick up. So you see the magnetic energy coming out of that inductor, which goes down in frequency, as you could assume. But if you go near the hot loop, you will see now, okay, it's much higher frequency content than what you have here, the decoupling capacitors. Now, so you pick up the magnetic field these capacitors create, and can get an idea now where most of the energy comes from. It's actually a probe made by a company called Langer. It's on the market now, it's about $1,000. Even if you measure here at the edges where ground is normally, you would expect it's totally quiet. It isn't. You have to get actually offset area to get really to a quiet area. If you probe to the outside, you still see till 30 megahertz something, the output capacitors. I mean, don't get me wrong, that decoupling capacitors carry current, that's their job. Now, there's always a magnetic field, it has to, because they need to do it, but it gives you also an idea I mean, how much current and how much filtering action they actually still do. It's the same thing up to 300 megahertz. Wie ich das nicht. Why it doesn't work?
It's fine.
It's fine. Now it starts. Okay, yeah. Probably don't have any tone anymore. Probably go back to.
I mean, it was playing just fine.
Was playing was just fine. But
Yeah.
say, yeah, it plays. Oh boy, I don't see it. That's tough. Okay, the thing is 300 megahertz output capacitor, and you still see some little bit action. Due to the fact that it's only 0.2 millimeter in diameter and it's not too sensitive, so essentially if you see something that has EMI-wise usually a meaning, you could even get an idea how the decoupling distribution between these 4.7 microfarad and 1 nanofarad here is. So you can get an idea how these current is distributed over frequency. So that theoretically should be quiet, but if you're in the corner, it's quiet. It's also a quiet area. Also, okay. And now let's probe the backside. To 30 megahertz, no? So it should be quiet. But actually, if you measure at the output inductors here, you see now there's some current to the first inductor, which is closer to the switching power supply. And normally with this probe, you shouldn't see any energy in the first inductor, but there's still some. So that filter is a compromise. It's not optimal. And if you have an idea what we talked about today, you know now why. Because the two inductors are much too close together. They talk to each other. So this inductor carries current and creates voltage transformatory or magnetic coupling into these inductors. So don't place two inductors which are in series very close to each other. Remove them and make sure what you could do is that as the input capacitors here, they also still see energy on this probe, which is too much. So what you should do is actually move the filter outside, make sure that the first capacitor is maybe 90 degrees oriented to these two ones, and move these two filter inductors further apart. So that's the message. Same with the probe here with 300 megahertz. Fine. Then what I meant, I mean, with a little bit of equipment, you always can ask Mother Nature what's going on, and you get an honest answer. And this area should be quiet. If there's something like an overlapped holes, you can look through it. It would couple already here in the input filter and make it much worse. So it's low frequency content, and what we saw up to 30 megahertz mostly. This is the biggest issue there also. Is there anybody using field probes actually for EMI debugging of circuitry here in the room? So it's probably worthwhile to ask the boss and get a set and a spectrum analyzer available. Spectrum analyzer doesn't need to be the most expensive stuff. I think even if it doesn't have the EMI bandwidth with 9 kilohertz and 120 kilohertz, if you measure with 10 kilohertz and 100 kilohertz, it's usually good enough because when I got a qualitative idea, if you are half a dB off, nobody cares that area. And what you need with some of these probes will be an input preamp, an LNA, low noise amplifier. Actually, the Lange probe under the MSA has an internal amplifier as a probe tip and a bias T now directly at the spectrum to see that. Okay, that's actually our Hangzhou lab. Now we built up according to Cisco 25. Now, so you see Eason DOT, 150 centimeter harness, fluorescent periodic antennas, and we will build. We'll build additional labs in Detroit, Germany, and in Shanghai, and we are readily willing to support you on the EMI issues there. So it's true. Okay, that's pretty much what I had here.
Good.
Now I open up to Q&A.
If any questions on the line, go ahead and submit them through the Q&A function you see in Zoom. Any questions here?
One of the things like you mentioned the resonance circuit.
Yeah.
You mentioned how you can protect the switching circuit.
Mm-hmm.
But in parallel, but for example, we have supplying the DC bus. But if we move the resonance around,
Mm-hmm.
all of this analysis is now shifting. Spread spectrum is you cannot define spread spectrum. What do you suggest?
Yeah, the problem with I see is, if repeat the question, what I've understood is that you can't use spread spectrum in your SUR supply, or did you get it right?
No, we have a resonant tank, right?
Yeah.
A series of resonant tank.
Sure, you can't use spread spectrum on a resonant tank because it defeats its operation. I mean, resonant tank is essential in half bridge with an LC, and that's the resonant frequency on your switch node. Now will go with, say, your rectangular switch node, and you move the frequency into the resonance and back out. So you can't use spectrum in a decent way. So it means that's physics. Can't help on that one. If you find something which can tune your inductor or your capacitor, that you can, okay, but don't think. Next problem is your switching frequency is actually quite low, which means that the gain you would get with spread spectrum is also low. And because you're running at 110 kilohertz, you might only buy 6 dB or something by spread spectrum, and that's probably not worth it to go to a lot of effort.
Good question to that is, can we take any care in the output stage of the DC-DC in order to be affected by the
if you, I mean, you power
Christian, can you repeat
okay,
that?
repeat the question. You mean if you have a DC-DC which makes this voltage, no? So you have a DC to DC converter which actually creates this voltage from whatever 14 volt or so you can run this DC to DC converter spread spectrum. Nobody, because you have a DC intermediate circuit, because that's whatever, either it's a fixed voltage or it's something like 6 to 24 volt or something which is moving up and controlled, but there's no AC on that area. So this DC-DC can be spread spectrum. Why not? No problem at all. Only this guy can, because you're physically limited by your LC network.
So we have a question on Zoom, which is, we are looking to purchase a spectrum analyzer.
Mm-hmm.
It's a necessary tool for today's electronic designing process. What type were you using?
I use actually a Rohde & Schwarz FSL3. I bought, I think about a few years ago, over an sync on eBay. It came from Korea with calibration certificate. Was used mainly for, I think, cell towers. But I mean, you can use essentially any grade. If you have to do really pre-compliance measurement, I would go with one of the major brands which makes compliance or pre-compliance equipment. If you want to have a spectrum analyzer for a real EMC chamber, I would say, okay, go to the guys like Rohde & Schwarz, buy an ESR on ESRP. I mean, it's a big ticket, but you pay it once, and the FFT version runs really fast and it saves you time. If you need something for your lab, you can go with anything cheaper. You know, for Rohde & Schwarz, for example, these FSL3, FSL7. I think they have now an FSP series. Also, Keysight, former HP, makes a series which is available. That's this N44 something series. You have to look it up, but I wouldn't necessarily go to some oddball, cheaper component. I mean, if I'm a ham radio operator, no, I would buy a cheapo Regol, because you always can replace equipment performance with gray mass between your ears and time you set in. So with a Regol 8015A, or I would buy an 8032 because it costs a little bit better. But if you are decent in a company working, I would stick either to Keysight or Rohde & Schwarz, which balance to the later, maybe because I'm from Germany, but also because that you get for fairly decent money good EMI documentation software, and don't underestimate that, because you have to handle then limit lines and all these type of stuff. And I mean, as ham radio operator, no problem. I can spend half a year in coding, but if my boss pays me, I'd rather go and buy for 3,000 to 4,000 euro a decent time-tested and proven program, which the industry worldwide uses for documentation. Okay. So put it that way. I mean, as MPS, we don't make spectrum analyzers, so I mean, I can pretty open. That's what I would do, and I've looked into it. If he is below an ham radio operator, doesn't have any money at all, I could even go with an USB stick type SDR radio. So there's also a way to do that, but it would involve that he probably digs into half a year of coding to get any meaningful measurements out of it.
So the short answer is, if you have a budget, Keysight or Rohde & Schwarz.
Yeah. Now, if you have a budget, I would say Rohde & Schwarz, and if it's really not happening, then the Keysight. Now the problem is the industry is booming. Now, there's nothing on the used market, so you might wait for the next bust and then get some stuff cheaper. A lot of times you don't have the time, so okay. I would go then with something from those two suppliers.
Okay, thanks, Christian. Any other questions?
One of the things is wireless chargers are So I was thinking that, of course, you have resident tank there, and you want to operate in the resident frequency you want to move a lot, right? But in the meantime, you still have this hot loop on your left side with this starting to happen. So if we spread spectrum, it's not that much, which is helping faster, which is helping on higher frequency, and so you keep your working frequency, which is transfer power, but meantime, try to knock down some high frequency content. Is that something that working, or what's your comment?
I mean, in general, you have to keep these input quiet, and spread spectrum is one method to do that. But I don't see that a residual spectrum noise on this capacitor will help you for the resonant time circuit. So make this one as a very quiet DC converter. Here you can use spread spectrum. Now here that's determined just by the system.
We have full range.
Yeah, it's almost like depending on frequency you switch. If you're talking about 100K, it's not that bad, but it's with Qualcomm or whatever other switching programs in mind.
On the resonant side, we have we're 125 kilohertz we're speaking right now.
Okay.
But the Q factor is terrible because you cannot get only so much energy. If we have to improve that, we have to go to those higher frequencies. But if I do that, I'm boosting my DC-DC stage. If I do that, I'm introducing all the things that we just discussed. So it's still work on.
If you keep at that topic, the weird thing about these low frequencies at 150 kilohertz, if you go look at the far field, even with a ferrite antenna, you can't create enough energy that you do not pass EMI on the far field. Far field at 100 kilohertz would be several kilometers away. Because you had to go way over saturation, get enough energy out. But near field, you create an enormous amount of energy. I mean, that's all. I mean, you need to charge your iPhone, so it's or phone, Samsung, whatever, and that's near field radiation comes in. And typically, the challenge, especially on automotive, is they have relatively tough limits. No? If you only have office building limits, you're probably pretty good off, that you can get with a decent shape here. But in a car, it's way tougher because you are inside an enclosed environment, and the EMI specs of cars are way more severe than the CISPO 22 office specifications.
That's what F2N does right now is you have limitations for people who have tracers and time frequencies, AM, you have NFC here, your keyboard here, all are at different frequencies. So something challenging.
Okay. So what spec you try to meet to see if when it's charging has the same size?
So we're going to find HCC regulations to start with. That's what we've been given, right? Beyond that,
Even more.
yeah, and then they ask us, since it's inside the audio, to be away from the EMI. Those three have.
And easily, you have definitely here some non-linear component. Now, so even so, you have a fairly high Q. Now, Q would be sorry dual digits if you are lucky. Well,
We're at 52 overall.
yeah. So something you don't get 2,000 or something like that. No way. No? So it's 52, which means any non-linearity you have here in the switches and your body dials and so will create a little bit of harmonics here. And that are probably the ones which are killing you. It's not so fundamental. It's probably the 400, 500 kilohertz, 1 megahertz. You get also a nice fence of all the harmonics there. But I mean, for some reason, they pay you so much money. That's what I know it's not that easy.
Christian.
Yeah.
So 2 more questions coming in from Zoom. The first one is signal integrity analysis useful to do before PCB fabrication?
Definitely. If it's an issue for you that the signal integrity is an issue because you have high-speed digital signals, or you have a power plane for some big micro where severe requirements is, you have to look first into it. No? And then you make a schematic where you think, okay, now I can get away with this. And from that you make a PCB. Now, PCB has a lot to do with signal integrity. And typically, all the topics we talked today, you can directly also attack from an RF standpoint, looking into microstrip lines, the magnetic and electric effects. I mean, it's the same for Maxwell equations. So same thing applies, same ideas.
Okay. And then just a follow on to that, we use Altium Designer for a PCB layout, and it has the SI tool built in. Any recommendation for prefabrication analysis?
No, I've only the viewer now. I can't comment on that one. But with my experience, I wouldn't bet too much on the software capability of these tools to come up with good ideas. So.
Okay. Very good. I think now is a good time to go ahead and break for lunch. So thank you guys for participating in some very good questions, and I think you guys are very alert during this presentation. Again, we are going to make a copy of this available. Okay, you guys can relive this experience. We'll send you guys an email link with a download of the presentation as well as the Zoom webinar. And I apologize that the first 15 minutes of audio are going to be missing because we didn't realize we didn't have the microphone turned on until later. But it's okay. And then if any other questions, you know, we'll be at lunch as well. Come and find us. If you guys want to have any more extensive follow-up afterwards, we're here. So just let us know, but try to let us know by lunchtime, okay? Again, lunch is going to be over at the Westin. So you just go back downstairs. I guess you could go left towards the hotel. It's in the hotel. It's a restaurant inside of the Westin, first floor.
Is it in the restaurant or?
It is actually in the restaurant, and they've given us just a little breakout room. So the food is in the restaurant, and then I mean, you can sit anywhere you want, but there is also a special room set aside.
Okay.
And thanks everybody on the Zoom. We're going to go ahead and disconnect.